In the last class, we introduced what are known as parametric equations. We're just going to take it a little deeper today, and we're going to see how perhaps in applied mathematics they use parametric equations. So our goal today is just to use time as a parameter in parametric equations. There's an assignment on Google Classroom. You do have a GPS regarding projectile motion. All right. There is something that is known as a cycloid, and you may never have heard that before. Essentially, what we have is we have a circle with a radius of A. We are going to say that the circle is going to roll. It's going to roll with no slippage along a fixed line, which we're going to choose to be the x-axis. The origin, point O, is one of those points at which point P, which is a defined point on the circle, does come in contact with the x-axis. So once again, the circle is rolling, point P is rolling around the circle, and the cycloid is this curve that is defined by point P's location at any particular moment in time, the cycloid. The angle that is changing is what is going to be given as theta in degrees, but more importantly, t is in radians. Every point P is defined by its horizontal distance and its vertical distance. And as time goes on, the horizontal and vertical distance are changing. It seems like we have a good use for parametric equations, and this is what it would look like. All right, sorry about the changing of the orientation of the graph, but I had to do it to fit it better into the screen. Let's take a look at arc AP. And you can see that arc right there. What do we know about arc AP? We should remember that arc AP is the same as the distance from point O to point A. Make sure you take a look at a refresher when we first introduced arc length. What else do I know about arc AP? Well, I remember we had a formula for arcs way back in the day, and that is the value of the radius times the central angle in radians. Okay, so I think I can calculate arc AP with simple substitution. That is because the value of the radius is A, that is also A, and T we define to be the central angle in radians. So that means that arc AP is equal to A times T. So what do we know about A times T? Well, if arc AP is A times T, and arc AP is the distance from O to A, that means that the distance from O to A is also A times T. So we're keeping track of all these lines and arcs. What else do I know? Well, if I take a look at the distance from O to X, see if I can find that distance in there for you guys. This little distance right there, you guys can see it. What do I know about the distance from O to X? Well, if I think about it, that little distance is the distance from O to A, taking away this part right here, which is the distance from A to X. So the distance from O to X is the distance from O to A, taking away the distance from X to A. Okay, so far so good. What else do I know? Well, I know the distance from O to A, I've already figured out, is to be A times T. Do some substitution. Minus, now here's the tough one. What is the distance from X to A? Well, let's think about it this way. If I go up here, notice that the distance from X to A is the exact same distance from here to there. It's a rectangle. And this is now a right triangle. We are defining this to be vertical with a measurement here of T. And I'm trying to find this distance. So the sine of angle T is the opposite, which happens to be the same as X times A, over the hypotenuse, which is side A. The sine of angle T is this unknown over A, which means if I solve for this unknown right here, I get that it is a times the sine of t. Make sure you understand where this value comes from. Is this right triangle right in here? And I know that this is the same as that. Okay, if I take a look at this, there's a common value. It is that value of a. So by definition, the distance from O to x is going to be a times a quantity of t minus the sine of t. Things to take note. Number one, a is the radius of the circle, and t looks like to be this central angle, which is being defined in radians. To the next step. Well, what about arc A to P? This arc right here. What do we know? Well, once again, we know it's the same distance from O to A, as we talked about in the last slide. Therefore, arc A to P is by definition the radius times the central angle in radians. I am just redoing what we did in the previous slide to make sure you understand it. Therefore, the radius of this circle is A. Notice that's the radius and that's the radius. There, substitute A in for R and T in for theta, which is given in degrees, and I get A times T. So I now know that the distance from O to A is just going to be A times T. Well, now let's talk about the distance from A to C. Where the heck is point C? Well, C is the center of the circle. So now I'm talking about this distance right here. Well, I know that the distance from O to Y, right here, people, what is it equal to? Well, it is the distance from A to C, getting rid of the distance from B to C. That's what I know the distance from O to Y is. The distance from B to C, this one right here, well, once again, this is a right triangle. We used these two before, and now we're kind of taking a look at this. Let's see if I can catch this. There we go. And that one right there. There we go. It didn't really work out for me. There we go. Just never give up. Now, this is still a right triangle. Now I'm talking about this distance right here. So I know the distance from A to C, and I just want to get rid of this distance to get the distance from A to B, because that corresponds to the distance from O to Y. So what is this? Well, this has to do with the cosine function. The cosine of angle T is this adjacent side over that hypotenuse, which then gives me information about this adjacent side. So the distance from B to C is going to be A times the cosine of T. That's the beauty of trigonometry, coming up again and again and again. So how much is the distance from O to Y, which corresponds to the distance from A to B? Well, it is definitely going to be the distance from A to C, which we already know is a radius of the circle, which is A, getting rid of this distance from B to C, which we just figured out was A cosine of T. Once again, like I did in the previous slide, that means the distance from O to Y is equal to 1 minus the cosine of T. Now, what's important here? The distance from here to here just corresponds to Y. And the distance from O to X just corresponds to X. So what have you and I really done? We have found the parametric equations. X is defined by A times the quantity of T minus the sine of T. Y will be equal to A times the quantity of 1 minus the cosine of T. And I know what you're thinking. You're thinking, well, so what? Well, to you, I say, pretty stinking impressive. We are able to track the location of this point as the circle rolls along the x-axis with no slippage at any particular time t. I would argue you found the parametric equations for what is known as a cycloid, and quite honestly, that's just pretty impressive. Ladies and gentlemen, you need to develop an understanding and love for mathematics just for the heck of it being mathematics. Have a great day.